I want to talk about something that is actually one of my favorite topics in this class, and I'll have to do it so quick. So it's a little bit of a pain. But I want to talk about, I'm going to put this heading here, the semi-infinite solid. I'll tell you why this matters at all. Right. I have just showed you this. That is good for spheres and plates and cylinders, right? And you calculate Biot and Fourier. Then we said something really cool. If Fourier is bigger than 0.2, we use the first term of the series, which is very convenient, happy. If it is like less than 0.2, life sucks. You have to do infinite terms, and you don't want to do infinite terms. But there is a ray of sun in all this, because if the Fourier is very small now, right? And this is something that I'm going to put. Well, I'm not going to put here. But if Fourier is much smaller than 1, if Fourier is much smaller than 1, and I'm going to write it down in the board soon, now things change. And let me show you something interesting. Fourier number is alpha t over L squared, right? So, and if we say this is much smaller than 1, means I'm going to solve for L. That means when L is much bigger than square root of alpha t. So what am I saying here? Imagine we have a problem, a sphere, or a cylinder, or a plane wall, and I want to see heat transfer by conduction at some time. Can be 30 seconds, can be 1 minute, whatever you like, right? If the thing that is having this heat by conduction, if this characteristic size, this is L, this is in the direction of heat flow. If that length is much bigger than square root of alpha t, right? That means that Fourier is much smaller than 1. So this means when something is either very big or the time is very small, right? Either of those. Something can be enormous or the times can be very short. Then this is what happens. And I'm going to tell this to you intuitively, and we're going to write equations later, okay? Intuitively. If I put a lot of heat somehow, with a laser, for example, on top of that wall, do you think after the first millisecond, people on the other side of the wall realize anything was going on? No, right? So this is very important because for very short times, the heat didn't get through the wall. And if I were to write the equations of heat transfer, I don't care anymore if the wall was 6 inches, 12 inches, or 12 meters thick, right? Because all the heat transfer is happening near the surface, right? You follow what I'm saying? When the time is very short, right? So very short compared with the thickness of the wall. If I tell you the wall is a membrane of 1 nanometer in thickness, 1 second is very long, right? You would realize that. So when something has these very short amounts of time, you stop caring about how big the thing really is, right? And if I don't care if my wall is 6 inches or 6 meters, then I'm going to say something easy. Forget about the thickness and say it's infinitely thick. All right? It's a good old trick, but the good news now is we forget about the length, direction, the length of the body. Another good thing, if something happens so close to the surface, right? That means the penetration of heat is thin compared with the area, right? Now we are back in a similar situation when we studied the thin wall and the thermal resistance of a thin wall, in which if something is thin, right, actually doesn't need to be plain and flat. Could be a curved surface. because being so thin, it looks flat, right, in its surroundings. So now this semi-infinite solid concept is a super awesome thing, because not only I forget about the thickness of what we were talking about, but also I forget about the actual geometry. For example, if I'm going to put my finger on a hot pan, right? The time is going to take me until I feel the pain and realize my stupidity. That time can be calculated using the semi-infinite solid. I don't need to think that my finger is actually a cylinder or whatever else might be, right? So this semi-infinite solid that might look like such a crazy idealization because nothing is infinite, nothing is so flat, blah, 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 in reality is a very, very, very general thing. I'll tell you one more before I get into the equations. The semi-infinite solid is so basic to conduction, heat transfer, and there's some basic simplifications that make you extremely powerful, and all this without solving any equation. My advisor, when I was doing my PhD, he did and still does lots of consulting. His salary as a professor, that's his pocket money. The real money comes from consulting, right? And he called this one of these equations. I'm going to show you the $1 million equation, because without having to solve the differential equation, he could make sense about this penetration of heat in transient problems using this semi-infinite solid. He could explain so many things. Because we have this limited time, we'll go over some of the mechanics. But let me tell you, what I'm showing you now is extremely powerful. And it's also the foundation for the whole theory of convection, right? Although it might not seem so related, talking first about conduction in a semi-infinite solid and the flow of air next to a wall. Soon you'll see how they are pretty much the same. So the semi-infinite solid applies when the combination of size and time match this equation, right? If something is not smaller, not bigger, not much bigger than this square root of alpha t, maybe it's not semi-infinite. Maybe you spend enough time in which the heat reached the other end, right? So short times or large bodies. In a semi-infinite body, we're going to have our solid. And we're going to have an x-axis and temperature. I want to draw your attention to something. Do you remember where the coordinate axis, where the center origin of coordinates is in a wall, when we studied the wall in the slides we had before? Right? Where is when we were doing the infinite series, where is x equals 0? Do you remember? At the center, right? Now it's not at the center anymore. Now it's on the surface. Of course, the fact that we picked the center, it made sense for that problem. But now, I don't care about the center anymore, because the center is infinitely far, or far enough that I don't care anymore. So I'm left with only the surface to use as a center of coordinates. Keep this in mind, very important. So I'm going to pick as an example something like the wall is at initial temperature T naught. I'm using the same notation of the book. So we used Ti before, now it's T naught. Right. On the surface, let's say for now that the surface got hot, you get a temperature Ts, right? I want to bank on your intuition here. So I want to do a temperature profile at some time, whatever time we pick that is after 0, right? What does this temperature profile look like? Something like this? I don't know if that's what you were thinking. No, it is like this, actually. How do you imagine it? How did you? Well, you suggest a straight line, and actually that kind of makes sense. That was the case of the normal wall. The problem is if you have something infinite, You cannot be linear in something infinite because it will be infinite high or infinite low, right? So when something is so big that we can consider it infinite, then it has to be asymptotic. Has to, because as you go to infinity, it cannot keep changing. And just before this, what did the profile look like? Would have been something kind of steeper, right? Something like this, right? So let's say this is time 1, this is time 2, right? You see how this curve is getting deeper and deeper? This is what we intuitively call the penetration of heat. Our intuition already has this concept. But we get to see that when we get serious about it, it's kind of tricky because heat penetrated infinitely in this asymptotic way, right? And the surface is more or less the same temperature, depends on the boundary conditions, which we will see. But the heat somehow is going in, right? Do you remember when we have curves like this, what concept we brought to make sense about these asymptotic curves? So let me tell you what I suggest, and what I think is totally awesome, but the book barely touches on that. You take the tangent there, right? And you'd have a characteristic penetration. And then at a different time you would have, oops, this should be tangent, right? You'd have a different characteristic penetration, right? Let's say T characteristic, X characteristic 1, and here an X characteristic 2. No equations so far, but just trying to make sure we're all on board. Now I'm going to write the equation, right? If I want to calculate a temperature profile, I need to do some sort of calculation. And we're going to do, so what we're going to do is do our energy balance. And this is going to be an elemental energy balance. So the energy balance funny enough, this is exactly the same equation we wrote for the wall before, right? Now, a semi-infinite solid and a wall are two quite different things, right? But the equation is the same. So what is different? What is it going to change now if the equation I wrote is the same? The coordinate axis, yes. Boundary conditions, right? Boundary conditions is actually what make these things come alive. So give me two boundary conditions in which we all would agree, based on what I discussed here. How many do I need? How many do I need? 3, right? 2 in space, 1 in time. Let's start with time. What would that be? Temperature. Temperature is temperature of position and time in this case, right? So by 0 you mean 0 in time, right? For all x, right? This is T naught. Good. Another one in which we all would agree. How about this? When I go super deep in. T naught. Thank you. That's exactly it, right? Those two things are universal for all problems of semi-infinite. All right? So what are we saying? That initially things are at T naught, and also when we go deep enough, it's still T naught because it didn't know anything happened on the surface. Whether I heated it or cooled it, just doesn't know. All right? The last boundary condition is here. We are going to study 3 boundary conditions, as the book does. Actually, there are many others too. But we're going to worry about these 3 too, right? 1, constant temperature, constant TS. 2, constant heat flux. Let me give you an example. If I grab a laser and shine it against the wall, the laser has so many kilowatts per square meter. That's what I'm putting on my boundary condition, right? So this is another boundary condition that we're going to be studying. It's a common one. You're going to see this condition also comes up when we study convection. And then another condition that we seldom use but is in the book, that is a convection on surface. 3 boundary conditions, could be many others. Let me tell you, before we get any deeper, something interesting about these boundary conditions. For all the boundary conditions I ever seen in my life for this problem, including insulated surface, the penetration of heat, this penetration of heat is more or less the same in all cases. So this is super interesting because I'm going to go over 3 boundary conditions, and there are many more which are mysterious to us. But what I'm telling you is that if somebody asks you what is the heat penetration, and they don't tell you the boundary conditions, you still can give them an answer because any one you pick is going to be more or less the same. We're going to get deep into a constant surface temperature one because it's the easiest, right? But the other ones, from the point of view of heat penetration, are more or less the same. All right, so let's look constant surface temperature. This goes in the exam. This goes not only in the quiz too, but will be in the final. Promise. Here you have space. Let's say we heated up the surface, right? But the graph would be the same upside down if we're cooling down. This is the surface. What do we know for all cases? For all cases in this condition, and I want you to have an intuitive mastery of this. How does surface temperature vary with time? Thank you. It doesn't. I told you it's constant surface temperature, right? I'm not trying to trick you, but it's a type of thing you should be laughing at me, right? But the fact that you don't makes me very sad. All right, so surface temperature, constant. How does surface temperature vary in space? Well, it doesn't, right? Because it's the surface, right? And we're taking this down to be this 1D problem. Okay, we know that for all times, this point is there. We know something else. For all times, temperature deep inside is always the same. For all times, I'm going to be here, right? Intermediate times, which are where things matter, right? We're going to have things like this. So one of you suggested this is an exponential decay, right? Dude, looks damn close to an exponential decay. And I said, no, it's not. And I said the truth. But you know what? If you think about it as an exponential decay, you'll be essentially always right. It's just that the formula is slightly different. Another thing, another problem I have seen come a recurring problem. Doesn't this make you remember the exponential decay in lumped capacitance with time? Okay, but this is a temperature profile. This is in space, right? Lumped capacitance had a very similar curve in time, right? Let's not confuse those two things. One is temperature in space, the other is temperature versus time. Not the same. Okay, and here let's give it a name. What do they call it? A characteristic penetration, right? And if we have bigger times, we know intuitively it's going to be like this. We're not going to solve this equation, which, funny enough, in this case is very easy to solve, but we will not do it. And the solution to this equation, you have there the way they wrote it in the book. I'm going to write it like this. T of xt is T naught plus believe it or not, I'm writing the same thing here. All right, I will delete erase this part here. This formula I wrote here is exactly the same one as the one on the screen. There is one subtlety there, though. You see that there it says ERF, right? Anybody knows what ERF is? It's the error function. Who knew? This is exactly the same thing of cumulative probability. It's exactly the same function. And has nothing to do with cumulative probability, other than it happens to use the same mathematical function. Now, see what I wrote here, ERF C? Do you know what that is? Anybody knows what that one is? This is the complementary error function. This is 1 minus R. I like much better the way I wrote this formula. Because the complementary error function, this complementary error function is the one that looks like an exponential decay. The complementary error function. So if I write the error function here, the complementary error function, and let's say this is out of zeta, now that we know how the name of that thingy there, right? Looks exactly like an exponential. Well, not exactly, but so closely. One important difference. Do you remember in an exponential what the characteristic decay was? Where an exponential, if this was an exponential, where do I cut the axis in an exponential? It cuts at 1. But here it cuts at square root of pi over 2. This is 0.89. It's more or less 1, right? It's not all that far from the exponential. But it's not 1, exactly 1 as in the exponential. If we compare with this formula here, right? If I were to graph this curve here, right? Right? This crossing, right? This characteristic length. We have 1 minute. So please stay with me and then we go happy on the weekend. This crossing here, right, is when what is inside the error function is square root of pi over 2. Right? I'm going to put determination of xc, right? So I'm going to grab what is inside here, x over 2 square of alpha t equals square root of pi over 2. The math is high school math. It's just like being on top of what we are doing. Everybody follows what I wrote this thing? I grabbed this argument, and I said, oh, this argument crosses the axis when it's square root of pi over 2. And the cool thing, this would be xc, right? I can solve for xc then, and I get square root of pi alpha t, right? This is 1.77 square root of alpha t, right? It's more or less 2 square root of alpha t, and you'll see why this 2 is a useful number. What I have taught you is so important and so useful that some of you might be crying right this minute. And this is the reason we have solved. Well, okay, we're dealing with a problem that is transient, non-uniform, super complex. Everything is changing. And you can calculate now the penetration of heat in these very difficult conditions. If you wanted to solve the differential equation, you're up for a week of pain. But somebody solved the differential equation, and because we're even better than that, we figure out where this intersection is. And we can calculate the penetration of heat as something that is more or less 2 square root of alpha t. Amazingly important. You couldn't do that in any other way simply. So we'll stop here. We'll wrap this up. But this calculation here will also give us the convection coefficient later on.